quizá podemos cambiar en inglés. So let's wait a bit, a few more minutes. Okay, so let's wait an extra minute and then we will start.
Okay. You can tell me when I should start.
So just remember to the people to mute themselves when they arrived. And also for the PhD student to send me, or to the student in general to send me a message to let me know that they are here so I can check them. Okay, so let's wait an extra minute and then we will start.
You can tell me when I should start.
Okay, so maybe let's start now. So it's my pleasure to let Jose Eduardo Méndez-Delgado presenting his project that has been submitted today on Archive. And for his introduction, I will let César Esteban presenting him. So, thank you very much.
Good morning to everybody. It's also a pleasure to me to introduce you to Jose Eduardo Méndez-Delgado. Eduardo is Mexican. He was born in Morelia in the state of Michoacán. He studied physics at the Universidad Nacional Autónoma de México. In 2017, he came to study the Master on Astrophysics at the University of La Laguna, enjoying a full studentship from the Fundación Carolina for Latin American students. He got a contract of Astrofísico Residente here at the IAC 1 year later in 2018, being the first of his promotion of that year, when Eduardo began his thesis work under the supervision of Jorge García Rojas and myself. He also obtained a complementary scholarship from the Consejo Nacional de Ciencia y Tecnología, CONACYT, from Mexico, for doing his PhD work here at the IAC. He's now in the final stages of his PhD thesis, doing a fantastic work on the physical and chemical properties of ionized gas in Herbig-Haro objects of the Orion Nebula, as we will see in a moment. Since 2020, he has published 3 papers as a first author, 2 papers on his PhD topic, and a third one on the results of his master's thesis, the TFM, on the galactic radial gradient of helium in the Milky Way. In addition, he has been co-author of other 2 papers published by our group on the abundance gradients of the Milky Way. Eduardo is not only an exceptional researcher, but is also a person with a great culture and with many intellectual interests. Eduardo, it's your time.
Thank you very much, Cesar, and thank you very much to the seminar commissions to let me talk about our work. For those who do not know me, I am Jose Eduardo Mendes. I'm a PhD student, and I'm going to talk about our work on photoionized Herbig-Haro object in the Orion Nebula. Our work will consist of at least 8 articles in a series, which 2 of them have already been published. The last one is available in the preprints of the ISE since today, so it's like very recent, and I'm glad that by coincidence it is ready for today. So we can start with the basic, that it's what is a Herbig-Haro object. They are small emission nebulae associated to outflows from newly born stars. These objects are considered to be originated through a centrifugal magnetic launch mechanism from young stellar objects. Since their discovery in the 50s by George Herbig and the Mexican astronomer Guillermo Haro, several of them have been observed and studied. These objects have generally been found in neutral environments where the emission is powered by the released kinetic energy that heats and ionizes the gas. In fact, this is the general idea that the community has of these objects, ejections of materials from stars whose ionization has been originated in shocks. We can visualize the physical idea by thinking that the ejected material interacts with the surrounding medium in a very thin layer, which heats the gas, exciting it and ionizing it. While behind this thin layer, a cooling zone is formed, which release all the kinetic energy through the emission of collisional excited lines of metals and recombination lines of hydrogen and helium. It is common to find in the spectra of these Herbig-Haro objects that in neutral environments, that the emission of most ionized ions are present in the hottest areas where the shock has been stronger, and then in the areas that have been cooled, or in the areas where the shock is not so strong, we can find the emission of ions of lower degree of ionization. Knowing the chemical composition of these objects is in fact really difficult, because for this we need to know the electronic density and the temperature. But since they are not in equilibrium, there are several densities and several temperatures between each volume of gas that is emitting radiation. These jets can travel from few tens to several hundred kilometers per second. This phenomena that evolve, this is a phenomena that evolved on the human time scale. For example, I would show you a video of the evolution of the jet of H834, an object located in the constellation of Orion. I think we can see it now. This video has been made with the observation of the same objects over several years. And although it's not seen in the video, there is also a rather faint counterjet which emission is reshifted. Generally, it's expected that these Herbig-Haro objects have bipolar outflows. So if these objects are formed in young stars, one will expect that there will be a large number of these objects in H2 regions where there are many star formings. And indeed, that happens. Multiple jet gas can be found traveling throughout the gas of the Orion Nebula. But in this case, there is a significant difference. The stars of the Orion trapezium generate a very strong radiation field capable of ionize the surrounding gas with their emission of photons. This radiation field is also able to photoionize the gas of these Herbig-Haro objects, and then the shock between the ambient gas and the Herbig-Haro object merely serves to create a dense blow where we can apply the standard methods to derive physical condition and chemical abundances in ionized nebula. When the photoionization equilibrium dominates, the gas maintains a fixed temperature by heating, by photoionization, and cooling from the emission of lines, collisional excited or recombination lines, and free radiation. The radiation of the Orion Nebula is strong enough so that the energy input from the shock is in fact very small and in most cases negligible. And well, we made this GIF that show the path of H8 529 and some other Herbig-Haro objects with images of the Hubble Space Telescope taken in the central part of the Orion Nebula over 20 years. As we can see, the jet mainly moves from east to west, but there are also some other gas interactions that are moving towards different directions. So this is actually what we observe if we have enough resolution in all directions of the central part of the Orion Nebula. So the next questions are, why do we study the Herbig-Haro objects of the Orion Nebula? What are we gonna get? We want to know the physical conditions, the ionic composition of these objects, the relationship of these properties with the geometry, kinematics, and dynamics of the gas. We want to understand the origin of these Herbig-Haro objects and the relationship to the areas of high star formation in the Orion Nebula, such as Orion South. We also want to know the global impact of these shocks on photoionized gas, in particular in dust destruction process. And we will do this by studying these regions in as much detail as possible, analyzing the effects that have a major impact, not only in Herbig-Haro objects, but in ionized nebulae in general. The standard way to analyze the chemical composition of an ionized nebula is first to determine the physical condition of temperature and density. This is achieved by measuring some intensity line ratios sensitive to these quantities. Then, with the intensity of the emission of the ions, we can calculate their abundances by solving the equations of statistical equilibrium. The detailed knowledge of the physics of photoionized regions is important, since it is the basis, for example, of many relationships that make it possible to determine the chemical composition of galaxies, metallicities, or other physical properties. But there are still many problems to solve that can have a major impact on the physical interpretation that we make of the universe. For example, the discrepancy that exists between the abundances of the same ion obtained with the intensity of collisional excited lines and those that come from electronic recombination, or the discrepancy between the chemical abundances obtained from stars inside of H2 region and those obtained from the gas that is surrounding it, and because they can indicate the existence of physical phenomena such as temperature fluctuation, lump of different chemical composition, unexplored atomic recombination process at levels commonly populated by collision, and along etc. So we want to know what happens in these Herbig-Haro objects that are formed from gas ejection from newly born stars. It's like an intermediate state between the stellar and the nebular matter. These objects are ideal laboratories where we can test our methods to derive chemical abundances. With these objects, which geometry is observable and which we have that in principle have the same composition of the Orion Nebula under different physical ionization conditions, we seek to understand the physics of the interstellar medium. So we base our work on deep high spectral resolution spectroscopy of the Very Large Telescope and high spatial resolution from the Hubble Space Telescope. We are able to solve different kinematic components that are present in the gas. And here I show you a beautiful image of the Orion Nebula that show many Herbig-Haro objects. Let me try to point some of them. I think I cannot. Well, in the southeast part of the left image, we can see HH204, HH203, and some other jets that looks like bullets going out from the nebula. And this is an image that it's showing emission in ions of low ionization degree. On the right side, many of these objects with low ionization degree disappear, and some other appears, such as HH529, which has a very high ionization degree. And this is in fact a realistic image of what we'll expect from any H2 regions, several gas interactions. A quite different image from the strong Raman sphere that it shows at the center, that is like a spherical cow approach in ionized nebula. In this talk, I'm gonna focus mainly in two Herbig-Haro objects, HH204 and the system HH529-2 and 3, which are shown in this image, along with the position of our UV slit. I am also going to talk a bit about our preliminary results on HH514. So this is how we work with the UV spectra. In this picture, we have the position of the UV slit, Then we reduce the observational data to obtain the two-dimensional spectra, and we especially isolate the different kinematic components cutting the 2D spectra. In this case, we can see two different components, H8 in the cut 3 and 2 and H8 in the cut 3. We finally obtain one-dimensional spectra with emission from the Herbig-Haro objects spectrally separated from the main nebular emission due to the different radial velocity and our high spectral resolution. In H8 204, in addition to these two defined cuts, we also studied the pixel-to-pixel emission at the scale of 0.2 arcsecond per pixel. This allowed us to have a deep and detailed spectra with thousands and thousands of emission lines, which were carefully measured by hand. I mean, with the IRAF task S plot one by one. And an interesting thing about H204 is that in addition to the main nebular spectrum, we detect the spectrum of the diffuse blue layer, a new nebula and another nebula that is in the line of sight with a slightly lower velocity than the Orion Nebula. So we do with such rich spectrum. We have several lines whose intensity ratio is highly dependent on the temperature or electron density in the equation of statistical equilibrium. With the continuum emission in the Balmer and Paschen jumps, we can obtain the temperature of the hydrogen, ionized hydrogen. Once we determine the characteristic physical condition of each ion, we can obtain the ionic abundances based on the emission lines. We detect even many of the weakest recombination lines. Therefore, we can study the problem of the abundance discrepancy. But also with the spectral position of the lines, we can determine the radial velocity of both the Herbig-Haro objects and the Orion Nebula, while with the width of the lines, we can estimate the temperature of the lines and or the degree of turbulence present in the gas. So we can do many things with our rich spectra. And with the HST images, we can study the proper motions and trajectories of the Herbig-Haro objects by using images of the Orion Nebula obtained over several years. Furthermore, we can also estimate the spatial distribution and variation in the emission of some ions. So some results of what we call the paper one, since it's a series of papers it's on our study of H8 529 2 and 3 and give several results. But the first thing that I put here is that the contribution of energy by shock is small and can be neglected. And how do we know this? Because we calculate the contribution of the shock and the contribution of the photoionization equilibrium radiation. On one hand, the flux from the cooling zone that is originated after the shock passage has to be equal to the kinetic energy released by the shock that we can calculate. And on the other hand, the radiative flux of the gas in equilibrium is proportional to the square of the post-shock density and the thickness of our work surface that we also can calculate. So once we verify that the spectrum of the Herbig-Haro objects it's consistent with that of a small scale H2 region, we studied with the usual ionized nebula method. We verified the absence of emission lines of neutral elements, and we noticed a high degree of ionization. We were able to analyze in great detail the composition of highly ionized ions as neon twice ionized and oxygen twice ionized, both in collisional excitation lines and recombination lines. We showed that the most likely scenario is that H8 529 2 is an internal shock from the same Herbig-Haro object and not a working head. As shown in the image, several knots are integrated within the US slit. We also determined that the flow angle with respect to the sky of the plane of the sky is around 58 degrees. So it shows that a significant part of the gas from this object is traveling towards the observer. The compressed gas of the Herbig-Haro object also increase the density, which it's around 30,000, about 3 times higher than the density of the Orion Nebula in the surrounding areas. However, the temperatures of high and low degree of ionization ions are consistent with the values obtained in the Orion Nebula due to the photoionization equilibrium. So we determine the abundances of several ions, but thanks to the high degree of ionization, we could calculate the abundances of helium, carbon, oxygen, chlorine, argon, and iron without any ionization correction factors. These ionization correction factors, or ICFs, are relationship based on predictions of photoionization models or similarities between the ionization potentials of some ions that calculate the contribution to the total abundance of the ions whose emission is not present in the spectrum. These factors, although very useful, have significant errors and uncertainties. So we detect several recombination lines of carbon-2 twice ionized, neon twice ionized, and oxygen twice ionized. With the latter, we calculated the electron density of the gas, and we obtain a discrepantly low value. On the other hand, we calculated the electronic temperature with helium lines, and we test the paradigm of temperature fluctuation of Painberg, and the results show that this paradigm is not capable of explaining the abundant discrepancy observed in Herbig-Haro HH200 and 529, 2, and 3. There seems to be another phenomenon causing the abundant discrepancy. We also observe slight overabundance in heavy elements with respect to the abundance obtained in the Orion Nebula. Although the shock can destroy dust and release part of the abundance of these elements in the gaseous state, this overabundance also affects some noble gases which are not depleted into dust. So this overabundance may be due to an inclusion of hydrogen deficient material from the peripheral area of the accretion disk of the source of HH529. However, this hypothesis requires further analysis. So the shock passage is capable of destroying dust grains, and these grains have higher content of refractory elements such as iron and nickel, which we observe an increase of a factor of 2.35 with respect to the abundance obtained in the Orion Nebula. It's interesting to analyze the level of dust destruction in each object and to know what factors favor this process, such as flow velocity or degree of ionization. So now I want to talk about some results of HH204. This object is located southeast of the Orion bar, near to Theta 2 Ori A, and in this case, in the plane of the sky. In this case, in addition to the analysis, to a similar analysis that done in HH529, 2, and 3, we studied the emission pixel by pixel at the scale of 0.2 arc seconds. We find, first of all, an steady increase of density when we approach to the bow shock, reaching values of 20,000, higher than the nebular values that are around 1,000 in the position of our slit. Pixel by pixel, we also derive the temperature of nitrogen and the temperature of sulfur that are approximately constant around 9,000 Kelvin. Since these ions are representative of the low and high and intermediate ionization stages, this implies that they are in photoionization equilibrium. However, the temperature of oxygen 3 that is representative of the ions of high ionization degree shows a prominent gradient. So here we can see where is the 0 point of our study, that it's close to the nose of HH204, and we can see how the physical conditions are changing with the radial distance. So this extraordinary behavior in the forbidden O3 emission can also be detected in the Hubble Space Telescope. A narrow border of high ratio of O3 and H alpha can be observed. The interpretation of these results it's based on the contribution of the different layers of HH204. The shock dissipates the kinetic energy that hits the gas and forms a cooling zone out of a photoionization equilibrium. The length of this cooling layer is inversely proportional to the density, and in our case, it's very thin since we have a very dense gas. The gas then cooled down and reached the equilibrium in the back layer of and in the jet. These last two zones that already achieved the photoionization equilibrium essentially contain ions with low and intermediate degree of ionization. Therefore, any emission that comes from the cooling zone of ions such as oxygen once ionized with respect to the contribution of the layer is negligible with respect to the contribution of the layers in equilibrium. However, the emission of the highly ionized ions basically only comes from the cooling zone. But we don't have to be scared about the shock. Its global contribution is negligible. We have estimated that the proportion of is less than 1%. We have been able to determine the temperature of oxygen 3 and the abundances of oxygen twice ionized due to the deepness of our spectra, but their emission is rather very faint. As we can see, the abundance of oxygen twice ionized is at least 2.8 index lower than that of oxygen once ionized. So basically, all the oxygen is only once ionized. And what about the other ionic abundances? Here we present the distribution of once and twice ionized ions of chlorine, sulfur, iron, and nickel. At closer distances from the bow shock, the density is very high, and the degree of ionization is basically zero. In these areas, the possible contribution of ions 3 or more times ionized to the total abundances is negligible. In fact, it is possible to see the relative increases of the abundances of the ions once ionized. As the ionic abundances of once and twice ionized ions get stabilized at distances approximately 5 milliparsecs from the bow shock, the contribution of ions 3 or more times ionized are null. And we can calculate the total abundances of these elements without any ionization correction factor with the greatest detail, with the greatest precision possible. We have been able to do this with oxygen, nitrogen, chlorine, sulfur, nickel, and iron. In fact, we also show that the iron and nickel have similar ionization and depletion patterns, which allow us to calculate the abundance of both elements by determining only one of them. On the other hand, the emission of argon twice ionized and helium ionized follow similar patterns. At closer distances to the bow shock, the density increased and the degree of ionization decreased. So the abundance of these ions decreased, and instead the abundances of argon once ionized and neutral helium should increase. In the case of nitrogen once ionized, at distances close to the bow shock, the low degree of ionization lowers the contribution of nitrogen twice ionized to zero. So we can determine the total abundance of nitrogen just with one ion. And what about the abundance discrepancy problem? Well, we don't have that problem, at least with oxygen. Both the recombination line and the collisional excited lines provide the same value, unlike what happens practically in all ionized nebula. There are several factors that may be key on this. Our detailed study reveals that there are no significant temperature inhomogeneities in the gas, and based on the known geometry of the object that flows at a small angle to the plane of sky that is traveling basically along the plane of the sky, it is likely that we are not integrating lumps of chemical inhomogeneities or gradients of density that we cannot solve. Finally, it is interesting that the majority of the studies of the abundance discrepancy problem are based on oxygen twice ionized recombination lines, almost all finding an ADF, while from the few studies that are based on oxygens once ionized, at least this work and the one of Méndez-Delgado et al. Of 2009 have a zero ADF. maybe not all ions have the same source of ADF. Our spectra is so deep that we have detected the emission of the deuterium associated to H204. It is the first time that it has been observed in a Herbig-Haro object. This is important because emission of this deuterium is produced mainly by fluorescent excitation from the far UV continuum in the interface between zones of neutral and ionized hydrogen. This indicates the presence of a trapped neutral zone traveling within H204. Furthermore, as we observe in the 2D spectra that I showed there, the distribution in the emission of neutral elements is different from that of ionized ions. It is shielded from the back, which is actually in direction towards theta Ori 1c. This indicates that the density increases so much that the degree of ionization is so low and traps an ionization front. Previous works that had studied the mixed spectrum of H204 with the Orion Nebula that is made with low resolution spectra has suggested that the emission of neutral elements was due to an interaction of the Herbig-Haro object with the neutral veil of the Orion Nebula. And it's common that sometimes we interpret the presence of a strong emission of oxygen or neutral elements, oxygen 1 or neutral elements in terms of the presence of a shock heating, but this is not always the case. Here we prove that in our case, we have a trapped ionization front. But in addition to the physical and chemical conditions, we want to know the origin of H204. The origin of many Herbig-Haro objects have been studied in the area called Orion South, within the central zone of the Orion Nebula, which is rich in young star formation. Due to the apparent proximity, it also has been speculated on a common origin between H204 and 3. However, we show that H203 is actually the superposition of two gas flows with different degrees of ionization and different origins. One that is coming from an area close to the trapezium and one that is coming from Orion South. Although we do not have enough evidence to clearly define the origin of H204, we define a flow that seems to connect it with the southern zone of the Orion South. We also show that the jet of H204 it's propagating at a small angle of 32 degrees with respect to the plane of the sky. Now, I will talk about an issue that is important for many studies of ionized nebula. In particular, for those who work with planetary nebula or high-density regions, and even for those who determine galactic metallicities by adding the emission of several H2 regions. Sometimes we take for granted that the sum of the spectra of several components will always give us a spectrum from which we will obtain an average representative values of the added components. Well, this is not always the case. We now explore the results that we will have if we have low or intermediate spectral resolution. For doing this, we mix the different kinematic components found in our slit, the emission of the Herbig-Haro H204, the diffuse blue layer, and the main nebular emission, and then we analyze the resulting spectrum. From the plasma diagnostic that I showed there, if we follow the classic procedures by taking the density of the diagnostics of oxygen 2, sulfur 2, and chlorine 3, that are the most classic ones, we will think that we are taking a consistent density, but in fact, this will underestimate the density, which also implies an overestimation of the temperature of nitrogen and an underestimation of the abundance of oxygen once ionized. And also, since the ICFs are based on the ionization degree, this implies an incorrect estimation of these ionization correction factors, and we will get incorrect chemical abundances in general, and we are not going to be able to correctly interpret the physics that it's involved. In fact, H204 had been studied in previous work with IFU spectra of lower spectral resolution as MUs or PIMAs, and these studies had found a very high temperature of nitrogen that was interpreted as shock heating. However, in reality, the problem is that the density is underestimated. In fact, the shock heating of the temperature of oxygen 3, which we show that it's significant in HH204, goes unnoticed in this low resolution spectra. But why these classical density diagnostics underestimate the density of the low intermediate resolution spectra in first place? The sulfur 2 and the oxygen 2 diagnostics has a very low sensitivity at values higher than 10,000. So the high density of HH204 goes unnoticed. They are basically blind to that. And on the other hand, although the chlorine 3 diagnostic has higher sensitivity in this range of densities, the low degree of ionization of HH204 provides little contribution to the total emission of chlorine lines in the simulated intermediate resolution spectra. So this diagnostic is also biased to the values of the main nebular emission. So a good way to detect the high density inclusions from a Herbig-Haro object in a low resolution spectra may be the use of the iron 3 lines as a density diagnostic. They will be biased to the density of the Herbig-Haro object because their sensitivity is practically nil at values lower than 1,000. And due to the destruction of dust with content of iron in the bow shock, most of the iron emission will come from the Herbig-Haro object. As we can see again from the plasma diagnostic, the iron 3 line diagnostic seems to be inconsistent with the three most classic ones. And sometimes these inconsistencies of the iron density diagnostic have been interpreted as failures in the atomic parameters, whether the transition probabilities or the collisional strengths. And this is an idea that sounds reasonable given the complexity of the ion with so many relevant levels. And we have explored this hypothesis in our work, given the geometry of HH204 moving at small angle with respect to the plane of the sky. We do not expect to obtain density gradients along the line of sight since we see the jet almost traveling transversely. Major density change can be resolved in the plane of the sky. We also have enough spectral resolution to separate the emission of HH204 and that from the Orion Nebula. So we have a single gas component with a low degree of ionization and no temperature fluctuation in at least 99% of the gas. So we use the temperature and density from several diagnostics, which were all totally consistent, and we compare the theoretical prediction of the intensities of all the observed lines, which are around 33, with the measured intensities. And with the data used, with the atomic data used, only 4 lines had differences greater than 10%. So the atomic data used is very reliable, at least for the HH204 conditions. In fact, we compare more recent atomic data that claim to eliminate inconsistencies with other diagnostics. This data gave us, in fact, full results in our case. We have to be careful when trying to eliminate these apparent inconsistencies. So coming back as a conclusion, we recommend analyzing all the diagnostics of the spectrum and not only adopting those that look consistent between each other, because we could be consistently wrong, but better and easier if we have spectra with high resolution. And what did we do with the nebular emission? We also studied it. I thought I didn't mention it in this talk. There is a detailed analysis of the nebular emission in each of the papers, but something that is notorious and that I'm going to mention is a special nebular component, the diffuse blue layer. Although it's present throughout the observed slit, in contrast, the contrast it's better in cut 2 without the presence of the strong emission of HH204. As we can see in the 2D spectra, in the oxygen 1's ionized line 3329, there is another component, intermediate component between the Herbig-Haro object and the nebular emission. this is the diffuse blue layer. And we can see some of the representative lines of this object. So we analyzed it and we found that it has a very low density compared with the Orion Nebula. This nebula is moving away from the molecular cloud of the Orion Nebula at the speed approximately of 28 kilometers toward to us. It presents emission of neutral elements, which indicates the existence of an ionization front. Its emission is mainly given in low ionization stages. This region is probably ionized by a star as theta 2 Ori A, or a cooler star, or even a cooler star as theta 2 Ori B. However, the presence of O3 emission indicates the presence of energetic photons that will need another source, probably the Orion Nebula. And this issue needs more studies. But we studied by the first time the chemical composition of this layer. So a short summary of HH204 results. We find that 99% of the gas is in low and intermediate degree of ionization, where the contribution of shock is negligible. We completely unveil the emission of HH204, finding an increase in density at shorter distances from the bow shock, while the representative temperature for the 99% of the gas was kept in equilibrium and without fluctuations. The degree of ionization is low enough to trap an ionization front, complementing the abundances obtained in HH 529, 2, and 3. In this object, we were able to determine the abundances of oxygen, nitrogen, chlorine, sulfur, nickel, and iron without an ACF. The abundance of oxygen deserves an important discussion. Since both the recombination and the collisional excited lines show an abundance consistent with 8.6, we could say that this is one of the most accurate oxygen determination that exists. It should also be considered that the dust with oxygen content must be partially destroyed in the bow shock, as we show with the increase in the abundances of iron and nickel with respect to the nebular values. Therefore, the abundance that we obtain in HH204 should be greater than the obtained in nebular areas without shocks, that where the oxygen where the dust with oxygen content should remain. However, there are regions in the nebula where the recombination lines predict 0.dex larger abundances. In this sense, the nebular abundances obtained with collisional excited lines are more consistent with expected values. It should be noted that there may be differences between the ADFs observed with oxygen once ionized lines and those observed with oxygen twice ionized ions. This is a point that deserves more investigation and that we are gonna continue researching in the next papers. We cannot be conclusive, at least not yet. And finally, I will give you a preview of what is being cooked in the oven. The next target, H8514, shows an extremely high density, probably one of the biggest ones, around 250,000 particles per square centimeter. And it has a high ionization degree, and it has a high velocity, radial velocity with extreme dust destruction. The abundances of iron and nickel are close to the solar ones. So if we analyze this object, we may get the total abundance directly, the total abundance of iron and nickel of the Orion Nebula without any kind of problem of dust depletion. So I will give you the summary of the results. We analyzed the physical condition and chemical composition of photoionized Herbig-Haro objects in the Orion Nebula. The contribution of the kinetic energy, we analyzed the contribution of the kinetic energy of the shock in the emission of these objects, and is negligible. the photoionization equilibrium is dominant. And one thing that I want to point out is that we are trying to get the chemical composition of the Orion Nebula with the highest precision that we can get, since this Orion Nebula is also representative for the solar neighborhood chemistry. So if we can make this, we can fit our models of evolution of the chemical abundances in the Milky Way and get a better constraint on this knowledge. With the analysis of the Herbig-Haro objects, we can test our knowledge of photoionized nebula, changing the different ionization and physical condition, but fixing the chemical composition. And the sum, well, the one thing that I mentioned is that the sum of the emission of several objects not always give a representative average of the present condition. So we have to be careful and analyze with a lot of detail each spectrum. And we can see, well, if you are interested, you can see the paper 1 that it's published, and the paper 2 that it's published. It's already published. We can see it in the preprints of the ISC. So if you want to take a look, you can do it right now after the talk. And meet our team. This is the team that we are working in this topic. Cesar Esteban from the ISC and Jorge Garcia Rojas are my supervisors. And William Henney is a collaborator from the Institute of Radioastronomy and Astrophysics of the National University of Mexico. And Carla Arellano, that was here as a postdoc at the ISC too, that now is in Texas, is also collaborating. So if you have some questions, I think I can stop here. So thank you very much.
Thank you very much, Jose, for your really great seminar. So now I will take any question. So please raise your hand if you have any question for Jose. So I have a question. It's not at all my field, so sorry if it is a kind of a stupid question. But you are saying that you were able to measure the abundances from different elements without the ICF.
Yes.
And so I was wondering if you can invert it, if from the abundances that you were obtaining, if you were able to measure the ICF or to correct them with different variation, I don't know, of temperature or different ionization state, things like that, to try to update the model or to fit the model of the ICF.
We can like use the knowledge of this to try to make them better, but it's not likely to fix everything with just 1 or 2 points. We need several objects to try to fit a relationship between several quantities. So it's not very likely that with just 1 or 2 points we are gonna fix some problems of the ICFs. So we can do that after we get like 100 objects studied or something like that. Yeah, but it's not likely that just with the daily spectra of 1 or 2 Herbig-Haro objects are gonna make this.
And the abundances that you will derive if you were using the ICF, are they really different than from the ones that you are measuring?
Well, we can test those differences. We didn't do it in the papers because we didn't need to use the ICF, so we didn't test them. But we can do it, and it will be interesting. Yeah.
Okay. So, is there any question, Jose? No. No one is a participant. Have one. So. I have another one. You were saying at some point that you were destroying some dust, and I was wondering what kind of dust is it? Is that pH? Is that big grains, small grains? Is there any concern of that?
Well, there are different compounds that may be present in the ionized gas. peroxines, oxides, some other compounds that I don't remember, silicates, or I think they can be present too. And so these elements, like iron or nickel, are likely to be depleted in this iron dust. So when the shock pass, it like hit the gas and like make some turbulence that may destroy these compounds and pass their elements to the gaseous phase again.
Okay. Well, thank you very much. So as there is no more question for Jose, let's thank him again. And just if you want to meet with him, remember he's a member of the IAC, so let's hope that we will be able to speak with him around the coffee or at the IAC and direct. Okay, so thank you everyone for this really good talk, and let's meet tomorrow for an instrumentation talk again.